Okay, so let's start on this. So I'm going to give you sort of a flavor of the research that we are doing, and again, the goal is to you know to again introduce you to research in the area, but also to help you know more about ongoing research topics that if you are interested in following up, please contact me. I'm repeating something because I realized I didn't turn on the recording, so I'm just summarizing once again. So the work that I'm going to talk about is something that has been done here at Stony Brook over the last 20 years or so, with a large number of PhD and master's students. And the particular topics that I'm going to go in more detail are work that has been done in the last 5 or 6 years by some of the people who took the security course in the recent in the last 5-6 years. Okay, so we hear about these attacks all the time, and the number of these attacks seems to increase. And not only that, as you can see, Maersk is one of the biggest container shipping companies in the world, and they had a ransomware attack a few years ago, and they estimate that the lost business was about $300 million. So it's a lot of damage that's happening as a result of this. And key applications like WhatsApp are being targeted and used in surveillance attacks against activists and whatnot. So I am in particular very interested in a class of attacks that are called advanced persistent threats. The industry term for this is APT. And these are very sophisticated attacks that often are carried out over a long period of time. So many of you have heard about this Equifax attack, where the attackers broke into this credit reporting company and stole sensitive data over a period of several months. So we talked about intrusion detection techniques, and yes, everybody has deployed intrusion detection systems, but unfortunately, most of the time, even though these detection techniques are deployed and some alarms do go off, there are so many alarms that people don't really know what's really going on, and so these attacks are missed. Even though the attackers have been on the system for months, they are still missed. Okay, so the OPM attack in 2015 was particularly serious because the data that was exposed was the data that is used for processing security clearance applications. So if you are someone who needs to get access to classified or top secret information, then you have to submit an application, and it is this Office of Personnel Management which processes these applications. And they were targeted by attackers, and the attackers were again carrying out their activities over a period of 6 months, and they stole a lot of highly valuable information. And so one of the things that we are trying to do is to come up with techniques that can detect these long-running attacks. Of course, the best way to detect or stop these long-running attacks is by stopping the initial step of the attack. But in reality, the attackers do get through some of the initial steps. So one needs to understand the entire life cycle of these advanced attacks. So there is the initial compromise or exploit stage, where the attacker, either using some kind of a phishing attack, is able to get a foothold on a vulnerable system. Typically, the foothold they get is on like a end user laptop, because these are the systems that are least likely to be secured. And so, but then just there is no information on these initial systems that they get access to. So what the attacker tries to do is to spread from that initial exploit into other systems that store valuable data, right? So basically there are back-end servers, back office systems, and the attacker is trying to figure out how to get to these back office servers. And that is called lateral movement, moving from one system in the victim network to another system until they get to a place where they can have access to sensitive data, which may be like password data or credit card data, or trade secrets, or financial data, all of which can be used to profit for the attacker. So what the research we've been doing is looking at all of these stages and trying to make our system robust against attacks at each of these phases. Okay, so the very first thing you can do is try to identify and fix vulnerabilities before deployment. So we have I've had many students who work on this problem, and that's one of the areas of research that is continuing. Vulnerability exploitation and preventing that is another area that we have been very active in. We have looked at many techniques for mitigating buffer overflows, SQL injection, and cross-site scripting, and so on. And this is another big area of research. Then restricting malware behavior, because even if, so the idea here is that you want to try to stop the attack at an early stage if you can. So the very first stage is, of course, even before the vulnerability is there on the system. And if you can fix that, great. But if you can't, then okay, the vulnerabilities got into the system. Now you try to prevent them from being exploited. Now you're past that stage. The attacker has somehow exploited the vulnerabilities, and they have some malware that's running on the system. Now how can we limit damage that this malware can cause? And then the very last stage, where the attacker's malware is running, we have no our techniques to try to stop or limit damage haven't worked. So as a last resort, we are just simply trying to figure out what's going on and understand what the attacker is doing, so that at least we could potentially launch manual responses to some of these activities. So we have research targeting all four phases of this exploit cycle. And I'm not going to talk much about these two areas, right? So we talked already a lot about memory corruption and input validation vulnerabilities and techniques to detect them and stop them. If you're interested, there are several slides here that talk about some of the research we have done on these problems. So such as, address space randomization is some work that we did in our lab. Fine-grained code randomization is something that we did, you know, and a variety of techniques for detecting memory corruption exploits. That's another area where we have done a lot of research, and it's still continues to be an area of active research. Similarly, for input validation, you will recognize all these pictures from earlier slides that we have used in the past. And all of that relates to some of the work that we have done in the past. So, so what I'm going to do now is instead fast forward and talk about two areas where we have been doing research, most recently. And one of them is binary analysis and binary instrumentation. So in fact, I'm going to talk about two pieces of work. One that was done about 5 years ago by some of the students that took this course, 7 or 8 years ago. And another piece of work that's currently being done by someone who took this course the last time it was offered. So, so let's talk about binaries. So we have discussed some of the difficulties of working with binaries. So let's, given all those difficulties, why do we even want to work with binaries, right? So when you do research, sometimes you do research because in an area because it's the easiest way to make impact, right? So when you talk about binaries, well, binaries are the form in which all code is distributed, and therefore techniques that can work directly on binaries can be very easily deployed, right? So when you if you use Linux or Windows, whenever you download and install an application, or whenever your application gets a security update, you are, by and large, what you're getting is binary code update. And if some of your security defenses can directly operate on these binaries, then that makes it so much easier to deploy, okay? Another point about binaries is that, well, binaries means you have the complete code, right? Not just the application, but the application, the libraries, and the operating system, and all of the code is available to you. And therefore, you can take into account the interaction between all of the different modules of code in designing your defense. And that's another advantage of working with binaries. And finally, there is this notion that binaries, you have the code that actually executes. So what you see is what you execute, right? So that's something you get when you're working with binaries. But if you are deploying a security defense on source code, you don't get that benefit, right? Because compilers can perform optimizations that can remove some of the code. And therefore, even though there may be certain operations and certain checks in source code, there's no guarantee that those will survive in the final code that runs. So that's another reason why you would work on binaries. And also, finally, if you are doing research, one reason for working on binaries is because it's working with binaries is non-trivial, right? So when you're doing research, you want to do things that are challenging, because solving a challenging problem is part of the appeal of doing research, right? So it's not just impact, but it's also you know, the accomplishment that comes from solving a difficult problem. So now let's understand, let's summarize some of the primary difficulties of working with binaries. One of them is the complexity of instruction sets. So x86 instruction set has thousands of instructions, and in addition, there are many extensions to the instruction set that are added for dealing with multimedia, cryptography, and various other problems. And so if you are trying to analyze and instrument binaries, you really need to understand the semantics of every instruction. And if the instruction set is very complex, then that makes your problem very challenging. The second is performance overhead. So you would have seen when you, most of you probably have tried to run pin with, if you try to run pin with any complex application, you would see that it's slows it down by a major factor, right? So it's not unusual for programs to slow down by a factor of 10 to 50, right? And that's not how security is nobody's going to accept that kind of slowdown for security. So the problem, though, is that the techniques that you have used so far and the techniques that are robust are all these dynamic instrumentation techniques, but dynamic instrumentation techniques are very slow. So the question that we have been looking at is, can you do static instrumentation, which can be much faster? And can we address the challenges of static binary instrumentation so that it can be robust on arbitrary binaries? So what I'm going to do in the next 10 minutes is to talk very quickly about one of the papers we wrote about 5 years ago that addresses this problem of instruction set complexity. Okay, so the typical approach for binary instrumentation is that somebody, the developer of the instrumentation system, has to sit down and figure out the meaning of every instruction, and the semantics of every instruction is manually encoded into the instrumentation system. And this is the kind of thing that you would see if you look at Penn or DynamoRio or Valgrind, and if you look at their source code, this is what you would see, right? And this is very tedious, and not only tedious, but also error prone, because, well, if you are trying to model the behavior of so many instructions, it's very easy to make mistakes in the way you model the instruction semantics. So we asked the question, is there a cleverer way to deal with this problem, something that's not so tedious? Because if you're doing research, again, you want to do interesting things, right? You don't want to do something that's just a lot of grunt work, right? So you want to come up with a interesting perspective, an interesting idea that solves the problem without a lot of bulwark, right? So one observation we made is that compilers already have done much of the hard work that we need to do. So the compilers that we use today, like GCC and CLang, right? So these are some of the most common compilers we use. So these compilers typically handle multiple source languages and they can generate code for multiple target machines. And the way they do that is by going through a common intermediate representation, right? So they first translate source code into an intermediate representation, and then they translate the intermediate representation into assembly, right? So the advantage of doing this in two phases is that they can write different front ends for different languages, right? For C, C++, Fortran, and so on, that all work on the first part of this translation, and then they can write, different modules for the backend, one for each target architecture, right? So they can write one IR to assembly translator for, say, x86, another for, say, ARM, another for, yet another architecture, and so on, right? So this way, by doing this, devising this common intermediate representation, you're able to take n front ends, right? And then n backends, or rather m backends. And now you have to write n front ends and m backends. Now you can do, n times m configurations, and all of those can be handled. So the key point for us, though, is that because there is already this backend which is translating the intermediate representation to assembly, there is some implicit recording of the semantics of these assembly instructions in the backend of the compilers, right? Because in order to translate some intermediate code, which you can simply think of as machine independent assembly, right? So this is the intermediate code is nothing but it's very much like assembly, but it's not tied to any particular machine. And because the compiler already includes this knowledge, the question is whether we can somehow reverse engineer this knowledge out of the compilers and thereby avoid having to do this manually, right? And this is what we did. We developed what is called a black box approach, meaning that the technique is not based on pouring through the source code of a compiler and figuring out exactly what the semantics is, because that is again going to be tedious and error prone, and also if the compiler is updated, then well, you don't, this is not that useful. So instead, what the technique does is it uses the compiler as a black box. So the idea is that you compile many programs, and as you compile many programs, you can basically look at the intermediate code that is produced for different programs and the assembly produced for those programs, right? In fact, what you can do is you can get pairs of, here is the intermediate code and here is the corresponding assembly type of information. And from these examples, you can learn the mapping from intermediate code to assembly. And that's the technique we developed. So basically the idea here is you collect the training data, then which consists of RTL, which is the intermediate code, and assembly. So you collect these pairs, and a typical example looks like this. This is the assembly code. Subtract some number from a register, and the corresponding intermediate code looks like this, which basically says you take the register RBX, you add some number to it, and then the result is going back into the register, right? So so you collect the training data, you figure out the mapping, and using a procedure called parameterization, you find this mapping, and then we construct, we develop an algorithm for learning this mapping, Again, in the interest of time, I'm not going to go into the details of exactly how this algorithm works. If for those of you who are interested, you can look through the slides more carefully, or you can look at go to the my lab's webpage where you can find the paper that describes the technique in detail. And basically, what we are able to do is we are able to construct essentially and you can think of this as a finite state machine for performing a translation. The term transducer is used in the research literature for referring to finite state machines that perform this kind of translation. And basically what we were able to show was that, essentially almost the entire instruction set can be translated using this technique. And we have shown that the technique is sound, meaning that the semantics it derives is correct. And you can actually, if you're interested, you can actually download the code and try it out. So I'm going to stop here, and we will continue the discussion on Wednesday. There will be no quiz on Wednesday, and I will, we'll finish this up and summarize the course. And one other thing that we'll do probably either on Friday or on next Monday is to have a review session where we'll go over any questions that you may have. So that's all I have for today. If you have any questions, stay on and ask me. Otherwise, we are done.